So the next thing we want to look at is arc length, right? Now, we did most of the hard work for understanding arc length back in chapter 7 when we were looking at applications of integration. Just to remind you of the basic idea, right? We have some curve, right? And we want to find the length of the curve, right? And so we partition. So if we're writing y as a function of x, we're going to partition along the x-axis, right? If we're writing x and y as functions of t, well, we're going to partition the t interval, right? So we do it's the usual kind of argument involving partitions and Riemann sums. It's the similar story. But again, the main thing that I want you to remember is that what we should do is take a piece of the curve, and I'm exaggerating here, and we approximate a bit of curve with a line segment, right? And so we have delta s on this side, delta y on that side, delta x on that side, and we get the obvious relationship from the Pythagorean theorem. And so we kind of, we let the deltas go to d's because we're taking the limit of Riemann sums. And we get this infinitesimal arc length element. And you might recall that I said, well, one of the ways you can write it, and maybe this is sort of an abusive notation, but we can think of ds as like dx squared plus dy squared, right? And, maybe I'm cheating a little bit in terms of rigorous math here, but let's think about what this does for a second, okay? So you have this, and now suppose you have a parametric curve, okay? So imagine that this curve looks like, say, x is equal to f of t, y is equal to g of t. That's your curve, okay? All right. Well then, what does that tell me about dx and dy? Dx will be f prime of t dt. dy is g prime of t dt, right? So, yes, maybe this is informal, but it gives me the right answer. What is dx squared plus dy squared? Well, it's going to be f prime squared dt squared plus g prime squared dt squared. Factor out that dt, which is common, square root of dt squared dt. Again, not rigorous, but it's a notational trick that gets us to where we need to be, f prime squared, g prime squared. Whether or not it's rigorous, it is an easy way to remember this thing, right? And then dt on the end, right? So whether you have y as a function of x, x as a function of y, or whether x and y are both functions of t, you can always take this as your starting point, decide what your independent variable is going to be, write everything in terms of that independent variable, clean things up, and you're good to go, right? Now we just take this, integrate between the beginning and ending t values, we have our answer, okay? So that's the setup. Maybe we'll pause here, and then we'll come back, we'll do this example.